All right, let's see if we can finish out what we were talking about in the last lecture. We were at the end of that lecture to introduce the idea of the point particle system, and it's a way of accounting for energy and work done on a system and removing some of the parts of the system that you don't care about, like thermal energies and chemical energies, and trying to figure out what's happening to the center of mass of a system, a complicated system like a person flying through the air or a diver or all sorts of instances. So the point, if you have a normal system that might be a person or whatever, a complicated system, the amount of work that you do on the system from external sources, not internal work, causes a change in the energy of the system, and that energy can be a change in translational energy, a change in rotational energy, potential energy, all of those types of energies, thermal, chemical, so on. And these, of course, are kind of difficult to account for. But the one thing that you can observe in any system is the motion of the center of mass. And fortunately, we have something related, sort of related to the work energy theorem that allows you to deal with the motion of the center of mass. If I'm interested only in the change in the translational energy of the system, that is the translational energy of the center of mass, that is produced by the sum of all the external forces acting over the distance that the center of mass moves. And so this is a quite different energy equation than this one is. This is only looking at the motion of the center of mass. There's no potential energy in here. It's just the translational energy, the 1/2 mv squared. Okay, so this is accounting. So in accounting, you have to be correct, you have to pay attention, you have to keep your minus sign straight, and you hope that you come up with the right sum, and you have to check your work. So we should be doing the same thing with this. All right, so let's go back to the example I did in class of someone who's jumping, and see if we can make sure we can understand the accounting on this. So suppose we start off with somebody who's crouched down. There's a person. They're crouched down, and then they jump, and just at the point where they're about to leave the ground, they've raised their center of mass. This is the center of mass here. They've raised their center of mass by some height h, and they started off with the velocity of the center of mass is equal to 0, and over here they've got the velocity of the center of mass is equal to v final. So this is just at the point where they lose contact with the ground. After they lose contact with the ground, of course, the center of mass is acting like any object in free fall. It'll go up and then come back down. Like any system, we have to define the system, define what the external forces on the system, and then account for them properly. So I'm going to define my system as the person that is jumping, and the external forces that are acting on that system are the force of the ground, F sub g, and the force of gravity, which acts through the center of mass, mg. And so the total force I have is going to be Fg minus mg, where I've defined up as the positive direction. Okay. Now, if I look at this naively, I would say that the ground is not doing any work on this system because the ground is not moving. It is a force exerted on the person's foot, but it's not doing any work. Of course, gravity is doing work on the system because the center of mass is moving upwards. Also, I know that there's a lot of internal work going on in this system, and there's a lot of energy changes such as moving of arms and such, and those are all sorts of things that I really can't account for. I get hot as I jump, all these things come in, so there's thermal energy. But by using the point particle idea, I can at least calculate what this velocity is just as I leave the ground. From the point particle point of view, I would say that the change in the translational kinetic energy of the center of mass is equal to 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared, which was 0, okay? And that has to be equal to the sum of the external forces acting upon the mass times the distance that the center of mass moved, or delta x. Well, I just wrote here that the sum of all the external forces acting on the system is Fg minus mg, and so this would then become that the change in the kinetic energy, translational kinetic energy of the center mass is equal to F of the ground minus mg times the height that the person jumped and going from, or the height that the center of mass moved and going from the crouching position to the extended position, and that's just going to be equal to 1/2 mv final squared. That's the change in the translational kinetic energy. Okay, so that's how the point particle idea would deal with the translational kinetic energy. Okay, but there's the other way I could look at this is just look at this as an entire system and consider all of the energies in the system. Okay, so we're set with the translational kinetic change in the translational kinetic energy.